Okay, so in this video, we are going to go through a numerical example of how to handle discharging transmission lines, but in the same process, this will also help us with setting up and solving bounce diagrams and tracking voltages at the load and at the source. So this will be a very good sort of general review for everything that we have done so far in this transmission line section. All right, so let me just remind you of the steps to solve these transmission line problems we're going to follow. The first is we pretend there's no transmission line and determine the load voltage and current on the line. We're going to determine the initial conditions of V positive and V negative, the net positive and net negative going wave that must exist in order to satisfy the steady state. Then we're going to figure out which one is going to change, and then we'll figure out what the new value is. Take the delta of that and we'll plug that into a bounce diagram as a new wave and we'll track it. All right, so let me set this up, and here is the problem that we are going to cover. We have a 5-volt source connected to a 100-ohm resistor. We have a transmission line with 50-ohm impedance. And at the load, we have it connected to a 100-ohm resistor. Okay, what's going to happen is at t equals 0, we're going to, let me change that a little bit. At t equals 0, we're going to switch that load, and instead of it being 100 ohms, we're going to switch that to connect to a 25-ohm resistor. All right, so that's at t equals 0. We're going to flip this switch, so the load, instead of being 100 ohms, becomes 25 ohms, and we're going to ask the question, what happens? Okay, so step 1 is determine the initial voltage and current on the load. Okay, so for that, we're going to take simple circuit, 5 volts, 100 ohms, and 100 ohms. Okay, we've got 5 volts, 100 ohms for the generator, and 100 ohms for the load before the switch is flipped. And so this would imply a load on the voltage of 22.5 volts, since the 5 volts is evenly divided between the 200 ohm resistors, and we have a load current of 25 milliamps, right? This is 5 volts divided by 100 ohms plus 100 ohms. All right, so that works out to be about 25 milliamps. All right, so that's step 1. We've got our initial conditions in terms of voltage and current on the load. Step 2 is now to figure out what are the steady state values of the positive and negative going waves that must exist in order to support this. All right, so let's go V positive equals VL plus Z0 IL divided by 2, which equals 2.5 plus Z0 is 50 times IL. IL is 0.025, and all that divided by 2. And this works out to be 1.875 volts. All right. Let's do the same thing for V negative. V negative is VL minus Z0 IL divided by 2, which equals 2.5 minus 50 times 0.025 divided by 2. Plug in those numbers into a calculator. It works out to 0.625 volts. All right, let's stop here and do a couple of sanity checks before we move on. All right, first, let's figure out what the load resistor is beforehand, right? The reflection coefficient at the load beforehand, right? To do that, we're going to take the 100 ohms of the load and divide it by, and subtract the transmission line impedance and divide by the sum, 100 plus 50. This works out to be 50 divided by 150, so that's 1/3. So the reflection coefficient at the load side is 1/3. So it shouldn't be surprising that the negative going wave is also exactly 1/3 of the positive going wave, right? Because V positive hits the load and becomes V negative, right? And so you got a ratio there of 1/3. So that's good. Let's do one more sanity check, which is that gamma G equals 100 minus 50 over 100 plus 50. That's also 1/3. Okay. And so you also can see that V positive equals V negative times gamma G plus the voltage that's inserted by the generator, right? And the generator takes a 5 volts and resistor divides it between 100 ohms and 50 ohms, which means it's going to be 5 volts times 2/3 is going to be what's inserted into the circuit, right? The voltage that's being injected. So if we take this value right here, V negative, multiply it by 1/3, and add it to 5 times 2/3, this works out to be 1.875 volts, which is exactly what we expect, right? So this all seems to make sense. Positive going wave becomes negative going wave with the reflection at the load. Negative going wave reflects to become the positive going wave, but we also have to add in the voltage that's being injected by the battery. There's actually an interesting insight here, which is to a certain extent, the battery never really finds out what the voltage is at the load. It's always injecting only a positive going wave based on the resistor divider between 100 ohms and the transmission line impedance. It always does that. It never actually changes that. The only thing that changes are those back and forth reflections between the source and the load that helps us to get to steady state conditions. Again, that's a remarkable way to sort of rectify the idea of special relativity and information cannot travel instantaneously with the notion of the way we expect circuits to eventually behave if we wait long enough. All right, so we've obeyed our sanity checks. Everything looks good. We got a V positive and we got a V negative. Next question is identify what is going to change. All right, let me erase some stuff here and make some room. Almost done. Just for a little faster. It's probably a faster way to do this. Okay, so what is going to change? All right. Given that we are disrupting the conditions at the load side, we can expect that V positive is not going to change because that's still coming from the generator side. We don't instantaneously change that. It's the V negative is going to change because the V positive is going to reflect off of a load that will be disrupted, right? And so V negative will change. At the load. All right, so that's step 3. So now step 4, what is the new value of V negative going to be? All right, so again, V positive is not going to change. To do that, we got to figure out what the new value of the reflection coefficient is at the load. And the load resistor has changed from being 100 ohms to being 25. So that we're going to make this 25 minus the line resistance minus 50 divided by the sum 25 plus 50. This works out to be minus 1/3. Right, so the new reflection coefficient is negative 1/3, which means that the new value of V negative will be equal to minus 1/3 times our V positive. And V positive was 1.875. So the new value of V negative is going to be minus 0.625, right? The value was positive minus 6.25. And the moment we flip that switch, it's going to become negative 0.625. All right, so that's step 4. Now step 5 is we're going to ask the question, how much has the value of V negative changed? Right, it's gone from 0.625 to minus 0.625. That is a delta V negative of 0.625 minus negative 0.625, which is also 1.25. Okay, so that is an important value right here, 1.25. That's the value of the voltage that we're effectively going to place into our bounce diagram as a wave. I'm sorry, this I got this backwards. This is minus 6.25 minus minus positive 0.625. So this is actually a negative value because it dropped. It started out as positive 0.625 and became a negative value. So the delta there is negative. So this is the voltage wave that we're going to inject in our transmission line. All right, so let's set up the bounce diagram and solve it. All right, so here we go. All right, I'm going to draw in our load voltage that starts out at, just to go back up here and trace it, our load voltage starts out as 2.5 volts. And let's also trace the voltage on the source, which also is going to be the same 2.5 volts, because in steady state, we have to have the same voltage everywhere along the transmission line. So we got the same 2.5 volts on both ends at the beginning. All right. And let's draw in our reflection coefficients, right? This is after the switch has occurred. So we have a gamma G. This is the new value of minus 1/3. Sorry, that's not a gamma G, that's a gamma L. Just erase that, make it neater. This is gamma L, and we've got a gamma G, which hasn't changed, of positive 1/3. That's the reflection coefficient at the generator side. All right, so let's draw this out. Here is T equals 0. And we're going to inject a negative 1.25 volt wave into the transmission line. All right, so we got 1.25 volts moving this way. Okay, that wave will reach the generator side. It will reflect right here. And the wave that's going back in the other direction will be, sorry, this is a negative right here. This is a negative 1.25 volts. This negative 1.25 volts will reflect with a coefficient of positive 1/3. So this will work out to be minus 1.25 divided by 3 volts. All right, this minus 1.25 volts divided by 3 will reflect like this and go in that direction. And we're going to have positive 1.25 volts divided by 9. That will reflect again. You see where this is going. This is positive 1.25 volts divided by 27, moving this way. Decimal right there, and this will keep right on going. And you can keep tracing this. Let me add one more step. All right, and this is negative 1.25 volts divided by 81, and that's moving that way. All right, so here we can trace the wave and just keep right on going. Eventually the wave will die out, and that's when the circuit will reach its new steady state. But let's track what happens to the voltage on the load. All right, it starts out at 2.5 volts. And when this first wave is launched, the value on the load is going to decrease. It's going to change by negative 1.25 volts. So this becomes 1.25 right here. And it's going to stay at 1.25 volts until this negative going wave goes all the way to the generator, reflects, it comes all the way back, and then it's going to change. We're going to take this 1.25 and we're going to add the value of the incoming voltage, and we're going to add the value of the outgoing voltage. This will be minus 1.25 divided by 3, and we're going to add another 1.25 divided by 9. And this works out to be 0.972 volts. All right, let's carry that one more step. That wave reflects, it goes back and forth again, and for the second time, it gets back to the load for a reflection. And we're going to take this 0.972, and we're going to add the incoming wave, 1.25 divided by 27, and we're going to add up the reflected wave, which is negative 1.25 divided by 81. Anyways, this works out to be, I'll spare you the calculations, 1.003 volts. Okay, let's do the same thing for the source, just to show that all this is possible, right? The source voltage is not going to change until that wave, that first initial wave reaches, at which point it's going to go from 2.5, and we're going to add up the value of the wave that comes in, which is negative 1.25, and we're going to add up the value of the wave that reflects, which is minus, let me move this over. Right, we're going to take 2.5 minus 1.25, and we're going to add up the reflected wave, which is minus 1.25 divided by 3. That will be the value of the voltage on the source side of the transmission line in between t equals 1 reflection time and 3 reflection times. This works out to be 0.83 volts. Repeat this process again, 0.83 plus 1.25 divided by 9 plus 1.25 divided by 27. This works out to be 1.02 volts, okay? So now we can basically, if I ask you to plot the load voltage as a function of time, you can basically read off these values. And let's actually do that. Let's take a look. Let me zoom out and place that over here, and let's plot that. All right, so this is VL as a function of time. All right, and let's draw this in blue. It starts out at 2.5 volts, and here is t equals 0. Starts out at 2.5 volts, and then it drops to 1.25 right there. All right, so it's going to go about halfway down. It's going to stay there until t equals 2 reflection times, right? 2 delay times, 2 TD, at which point it's going to drop down to 0.97. Right, so this is 1.25 volts, and this is 0.97. And then, after 4 delay times, t equals 4 times TD, it will jump up to 1.003 volts. You'll notice that it seems to be oscillating back and forth. We're actually getting some ringing here, right? We know that it should steady out to a value of 1 volt. Let me go back to the circuit again. Okay, I've got 5 volts, and I've got a resistor divider of 100 ohms and 25 ohms. And so I know that after a very long time, we should end up with a voltage of 1 volt on the load, right? Because we've got this resistor divider. So we're expecting things to land on a voltage of 1 volt on the generator, sorry, on the load resistor. And as you can see, that does seem to be happening pretty effectively. right? We didn't get there immediately. We jumped down to 1.25, then we actually overshot and came back up and went too high. And this eventually is going to settle out, and it's going to steady at, if we wait long enough, 1 volt, right? And that's comforting to know that that's going to happen. Let's also track the voltage at the source side of the transmission line as a function of time, right? So again, it's going to start out at t equals 0. It's going to have a value of 2.5 volts. And the moment that switch flips, nothing changes on the source side because you got to wait until this initial wave propagates down to the end and hits. And so we got to wait until t equals 1 delay time, 1 TD, at which point it's going to drop down to 0.83 volts. All right, wait long enough at t equals 3 delay times. It's going to jump up to about 1.02 volts. This is not to scale, but hopefully you can kind of see what's happening. And here we go. Again, we can see an oscillation. We're expecting Vs to end up at 1 volt because at the end of the day, the transmission line should have the same voltage everywhere, the same 1 volt. And you can see we overshot, we went too low, then we went too high again, and eventually this is going to settle out at the same value of 1 volt. But again, it takes some time to get there. So once you follow these steps of determining the initial wave that's launched in a transmission line, even for a discharging case or for any disruption to the transmission line, all you got to do is put that back in the bounce diagram and track everything and just be very focused for 1 step at a time with each reflection and each change to the source and load voltages. And it will always converge to where you expect it to be in the simple case of there being no transmission line. If it doesn't converge there, you've done something wrong, and you can always use that as a sanity check. So if I had seen that this is going to 1 volt, and then I'd gone back to the circuit and said, oh, it actually should be settling down to 2 volts, I know I've done something wrong, and I can check my math or I can check my circuit analysis and try to identify the problem. All right, so transmission line theory always converges to the same solution that you are familiar with before this class. I know I've said that a lot, but it's a very important thing to emphasize. All right, so that concludes this video on initially charged lines or discharging lines. In the next couple videos, we're going to talk about pulses and sort of piece everything together. And then we're going to complicate things a little bit by considering sources that are not necessarily resistors, but also may have capacitors or inductors.